Module 5, Lecture A, Categorical Encoding. By the end of this lecture, you will be able to encode categorical features using ordinal and one-hot strategies, handle unknown, infrequent, and redundant categories in practical datasets, and integrate categorical encoders into ColumnTransformer workflows. Basic categorical encoders. Ordinal encoding. Ordinal encoding converts ordered categories into numbers so machine learning algorithms can use them. It is best for data with a natural ranking, such as education levels, satisfaction ratings, or clothing sizes. The assigned numbers do not have meaning on their own, but they preserve the relative order of the categories. Ordinal encoding is simple and memory efficient when categories have a real order, because it turns one categorical column into one numeric column. The main risk is that models may treat the assigned numbers as meaningful distances, even when the gaps between categories are not equal. It is especially unsuitable for unordered categories, such as city names or payment methods, because the numeric codes can imply relationships that do not exist. Ordinal encoding should only reflect a real order in the data, such as severity or seniority, so the numbers match the meaning of the categories. For unordered categories, one-hot encoding is usually safer because it avoids implying a false ranking. Whatever encoding is used, the mapping must be learned from the training data and applied consistently to all later data, including production, to keep model predictions reliable. Python code. Ordinal encoding. This example shows ordinal encoding, where ordered categories are converted into meaningful numeric labels. The result includes the learned mapping between each category and its assigned number. We import pandas to work with structured data in data frames, making the dataset easier to manage and analyze. We also use Scikit-Learn's ordinal encoder to convert ordered categorical values into numbers, so the data can be used by machine learning models that require numerical input. We create a small pandas data table with one column for shirt size, containing values such as small, medium, large, and extra large. These categories have a natural order from smaller to larger, making the dataset useful for demonstrating ordinal encoding, where ordered labels are converted into meaningful numbers. Before encoding, the code checks that the data frame includes the required size column. If it is missing, execution stops with an error, so the problem is caught early. This validation helps prevent later failures during the encoding process. Define the shirt size categories in their natural order, from smallest to largest, so ordinal encoding assigns meaningful numbers. Then create a Scikit-Learn ordinal encoder using that order, allowing each size to be converted into an integer based on its position in the sequence. The encoder first learns how each shirt size category maps to a number based on the chosen order. It then applies this mapping to the size column, creating a new encoded size column with numeric values. Converting these values to integers makes them ready for later analysis or modeling. A small data frame is created to show how each original category is converted into a numeric label. It pairs each category name with its encoded value from 0 through 3, so the encoded data is easier to interpret. The output first labels that the shirt data now includes ordinal encoded values, then displays the data with each size category and its numeric encoding. It uses a string display method to hide row indices for cleaner reading. A second message introduces the learned ordinal mapping, followed by the mapping itself, showing how each category was converted into a number. This script shows how to use ordinal encoding to convert shirt size categories into numbers for machine learning. It creates a small data set of sizes, confirms the size column is present, and defines the correct order from small to extra large. A Scikit-Learn ordinal encoder then assigns each size a numeric label and adds the result to the data. The output shows both the original sizes and their encoded values, along with the category to number mapping. One-hot encoding. One-hot encoding represents unordered categorical data by creating a separate indicator feature for each category. This avoids assigning numbers that could imply a false order or relationship between categories. It is useful for features such as city, product type, or payment method, helping models treat each category independently and make more accurate predictions. One-hot encoding represents categories as separate yes or no signals instead of numbers, so models do not assume a false order or ranking. This is useful for data like university majors or neighborhoods, where numeric labels could imply relationships that do not exist. By keeping categories distinct, one-hot encoding helps models learn from categorical information more accurately. One-hot encoding works well for categorical features with a small number of unordered labels, such as marital status. However, it can create too many features when categories are numerous, increasing memory use and making models harder to train and interpret. Because some encoded columns can be redundant, one category is often dropped as a reference. Overall, use one-hot encoding when the categories are distinct, unordered, and manageable in number. Python code. One-hot encoding. This example shows one-hot encoding, where each nominal category is converted into its own indicator column. The result includes the encoded feature names. We import pandas to work with structured data, then use Scikit-Learn's one-hot encoder to prepare categorical values for machine learning. The encoder converts categories into binary columns so algorithms can process them effectively. We create a small pandas data frame with two unordered categorical columns, payment method and shipping speed. These include values such as credit card, cash, debit card, standard, express, and overnight. Because the categories have no natural ranking, the data is ready for one-hot encoding, which converts each category into its own binary indicator column. The code verifies that the orders data frame has 4 rows and 2 columns by checking its shape. If the dimensions are different, it raises a value error to signal the mismatch. This early validation helps ensure the data is in the expected form before any further processing. We create a Scikit-Learn one-hot encoder that returns a dense array, making the result easier to use with pandas. The encoder is then fit to the categorical order data and transforms each category into its own binary column. This converts the data into a numerical format that machine learning models can use. We get the new feature names from the encoder using the original order columns, then use them as headers for a data frame built from the encoded data. This makes the one-hot encoded output easier to read and keeps each new column tied to its original category. First, we display the original categorical data before transforming it. A header labels the output, and the first 4 rows of the orders data frame are shown without the index for a cleaner view. This gives us a simple baseline for comparing the data after one-hot encoding. The output begins with a short message explaining that the one-hot encoded columns will be shown. It then prints a small sample of the encoded data by displaying the first 4 rows. The values are converted from floating point numbers to integers for readability, and the row indices are removed to create a clean tabular view. This script shows how one-hot encoding converts categorical data into a machine learning-friendly format. Using a small dataset with payment method and shipping speed, it turns each category into its own binary indicator column with Scikit-Learn. It then displays the original data and the encoded result, illustrating how categorical values become numeric features for modeling. Pandas categories. Pandas categories help prepare categorical data for machine learning by marking columns as values from a fixed set, such as product types or regions, rather than free text. They also make it clearer whether a category has a meaningful order like shirt sizes, or no order, like store locations. Using categorical types keeps data more organized, can save memory, and makes errors easier to spot before encoding. Pandas categories store repeated labels efficiently by keeping the visible category names separate from internal integer codes. Pause. This is useful for large datasets with many rows and only a few unique values. Pause. However, the internal codes are only for storage and do not represent order or meaning, so they should not be used directly in machine learning models. Pause. For modeling, use explicit encoding methods such as ordinal or one-hot encoding. Pandas categories help keep categorical data consistent, even when some expected values are missing from a sample. This is especially useful when splitting data into training and testing sets or applying a model to new data. Defining categories in advance ensures each subset uses the same allowed values, while ordered categories preserve meaningful sequences like risk levels, and unordered categories remain unranked. Python code. Pandas categories. Before applying machine learning encoding, inspect the pandas categories to understand the labels, their order, and the internal codes assigned to them. Remember that these codes are only how pandas stores the categories, not the final features used by the model. We begin by importing pandas, a key Python library for working with structured data. It provides tools such as data frames and supports efficient data manipulation, analysis, and transformation. We create a small pandas data frame with two categorical columns, color and size. Color contains unordered categories such as red, blue, and green, while size contains ordered categories such as small, medium, and large. This simple dataset sets up the need to handle unordered and ordered categories differently. The code treats color as an unordered category, so each color is a distinct label with no ranking. It then defines size as an ordered category, where small comes before medium and medium comes before large. This lets the size values be compared according to that specified order. The code verifies that the color column is stored as a categorical data type. If it is not, it raises an error to signal that the data must be prepared correctly before later operations that depend on categorical values. First, we inspect the data frame to see the first few rows and confirm its categorical data types. We then review the distinct categories for color and the defined order for size. Finally, we verify that size is treated as an ordered category, so the data structure is clear before applying machine learning encoding. Pandas stores categorical values such as color and size using internal integer codes, which can be viewed through the category codes attribute. These codes are compact and useful for pandas internally, but they should not be used directly as machine learning features. For modeling, the categories should be converted later with an appropriate explicit encoding method. This script shows how pandas handles categorical data using shirt colors and sizes. Colors are treated as unordered categories, while sizes are ordered, and the script checks their category settings. It also shows the internal integer codes pandas uses to store categories, while emphasizing that these codes are not final machine learning features and should be replaced with proper encoders during feature engineering. Category handling. Unknown category handling. Categorical encoders must be able to handle categories that were not present during training. Real systems may encounter new customer regions, insurance providers, or other labels after deployment. If the encoder cannot process these unknown values, the model may fail instead of making a prediction. Preparing for unexpected categories helps keep the system reliable in real-world use. How to handle unknown categories depends on the encoding method and the feature context. With one-hot encoding, unknowns are usually represented as all zeros, which can work if they are rare or other features support the prediction. With ordinal encoding, unknowns should use a separate placeholder value, so the model does not treat them as having a meaningful rank or size. Handling unknown categories is a modeling decision, not just an encoder setting. Unknown values may be normal, such as new devices appearing in web analytics, or they may signal data problems like typos or outdated identifiers. The key is to distinguish real new categories from errors and to monitor unknowns after deployment, because rising rates can show that the training data is stale or the target population has changed. Python code, unknown category handling. This example shows how categorical encoders handle labels that were not seen during training. One-hot and ordinal encoders treat these unknown categories differently, but both can produce safe codes instead of failing. We import pandas to work with tabular data and use Scikit-Learn tools to prepare different types of columns for machine learning. A column transformer lets us apply separate preprocessing steps to selected columns, while one-hot encoding converts categories into machine-readable features. Ordinal encoding also handles categorical data by assigning each category a unique integer. We create a pandas data frame to represent the training data with two categorical columns, region and plan. The region values include north, south, east, and west, while the plan values include basic, plus, and premium, with basic appearing more than once. These are the categories the model learns from before it later encounters any new categories in deployment. We create a new pandas data frame to test how encoding handles categories not seen during training. It includes region values such as central and north, and plan values such as plus and enterprise, allowing us to check how the encoder responds to unfamiliar categories. The code verifies that the training data has 4 rows and 2 columns, and that the new data has 2 rows and 2 columns. If the dimensions do not match, it raises an error, saying that 2 small categorical tables were expected. This check helps ensure the data is in the right shape before processing continues. A column transformer is used to one-hot encode the region and plan columns. The encoder ignores categories not seen during training, representing them with all zeros instead of causing an error. Sparse output is turned off, so the transformed data is returned as a dense array for easier downstream use. A one-hot encoder first learns the categories found in the training data for each selected column. It then converts new categorical data into binary columns, with 1 column for each learned category. If new data contains an unseen category, that category is represented with zeros. The generated feature names identify what each binary column represents. An ordinal encoder from Scikit-Learn can be set up to handle categories it has not seen before by assigning them a reserved value, such as -1. After the encoder learns category to integer mappings from the training data, it can transform new data into integer codes. Any new category that was not in the training data is encoded as -1. We inspect the feature names and encoded outputs to see how the encoders handle new data with unseen categories. The one-hot encoder creates binary columns for known categories and represents unknown values, such as central or enterprise, with all zeros in the relevant group. The ordinal encoder shows its learned category mappings, then assigns unknown categories a reserved value of -1. This keeps unseen data from being mistaken for a learned category. This script shows how one-hot and ordinal encoding handle categories that were not seen during training. The one-hot encoder ignores unknown categories by producing all zeros, while the ordinal encoder marks them with a reserved value of -1. This lets new data be processed without errors while making clear how each encoder treats unexpected categories. Infrequent category grouping. Infrequent category grouping helps manage categorical features that have many rare values. Instead of encoding every uncommon category separately, rare values are combined into an other group. This reduces the number of features and makes the data less sparse, while still showing that those observations come from less common categories. Grouping rare categories helps models become more stable and generalize better, especially when data is limited. If uncommon categories are kept separate, the model may mistake random noise for meaningful patterns. Combining them gives a more reliable signal for sparse or varied data, and reduces the chance of overemphasizing categories with too little evidence. Choose the threshold for infrequent categories based on the size of the dataset and the goals of the analysis. Define it using only the training data, such as by a minimum count, a proportion, or a limit on the number of categories. Then apply the same rule consistently to new data. This helps handle rare and unknown categories reliably, while recognizing that rare categories may still contain useful information. Python code, infrequent category grouping. This example shows how one-hot encoding can group rare categories based on the training data. Any unknown values seen later are placed into the same infrequent category. We import pandas to work with data in tables and Scikit-Learn to access machine learning tools. From Scikit-Learn, we use the one-hot encoder to convert categorical values into a numeric format that machine learning models can use. We create a pandas data frame for training data, with one column for product brands. Some brands, such as A and B, appear multiple times, while others, such as C, D, and E, appear only once. This mix of frequent and rare categories prepares the data for using a one-hot encoder that can group infrequent categories together. A small, new dataset is created with one brand column to test category encoding. It includes a common known brand, a rare known brand from training, and an unseen brand. This lets us check how the one-hot encoder transforms both familiar and unknown categories. We use Scikit-Learn's one-hot encoder to group rare categories that appear fewer than 2 times. Unseen categories are also treated as infrequent when possible, so new or uncommon values are handled consistently. The encoder returns a dense array rather than a sparse matrix, which is convenient for small datasets. The encoder is fit only on the training data, so it learns the categories found there without using information from new data. This prevents information leakage and ensures the model's category handling is based solely on the training examples. During fitting, the encoder also determines which categories are frequent or infrequent, according to the chosen minimum frequency. The code verifies that the training data contains exactly 8 rows before continuing. If the row count is different, it raises an error to signal that the data setup is incorrect. This validation helps catch preparation issues early. First, apply the trained encoder to the new data so it uses the same encoding rules as the training set. Then, place the transformed values into a data frame with the encoder's generated column names, making the encoded categories easier to interpret and connect back to the original values. The output first confirms the Scikit-Learn version for reproducibility, then shows which brand categories the encoder learned from the training data. It also displays the resulting encoded column names and compares them with the brands in the new data, including unseen ones. Finally, the encoded table shows how each new brand is mapped, including how infrequent or unknown brands are represented. This example shows how Scikit-Learn's one-hot encoder can handle rare and unseen categories. It learns which product brands are common in the training data and groups brands that appear fewer than 2 times into an infrequent category. When new data is transformed, both rare brands and unseen brands, such as Z, are encoded consistently as infrequent. This helps keep category encoding stable when future datasets contain uncommon or unknown values. Drop options. Drop options in one-hot encoding reduce redundancy by removing one category column, since it can be inferred from the others. This is especially important for models like linear regression, where redundant columns can make coefficients unstable. The dropped category becomes the reference point, so the model interprets other categories relative to that baseline. When encoding categories, the dropped category becomes the baseline for comparing all others, so it should be chosen carefully. Avoid using alphabetical order, because it may create an arbitrary or misleading reference point. A good baseline is usually the most common, most stable, or most meaningful default category. Choose drop options together with your strategy for unknown and infrequent categories. If rare values are grouped, decide whether the dropped category should be an original category or the new infrequent group, since dropping that group can hide rare category effects. Also ensure unknown categories are handled consistently, because an all-zero encoding may represent either the reference category or an unseen value. Overall, align the pipeline with the model type, interpretability needs, rare values, and future unseen data. Python code. Drop options. This example compares options for dropping categories in one-hot encoding. Dropping a category creates a baseline reference group, and unknown categories may be represented with all zero encodings. We import pandas for working with tabular data, and use Scikit-Learn's one-hot encoder to turn categorical values into a machine learning-friendly format. We also import Scikit-Learn, which provides efficient tools for data mining and analysis built on common scientific Python libraries. A training dataset is created with one payment column containing the categories card, cash, and debit, with card appearing twice. The second dataset uses the same payment column but includes card, cash, and a new category, crypto. This setup tests how an encoder handles categories it has seen before and an unknown category it has not seen during training. A Scikit-Learn one-hot encoder is created to convert payment categories into numeric features. It drops the first alphabetical category as a baseline, ignores unknown categories, and returns dense arrays. The encoder is fitted on the training data to learn the categories, then reused to transform new data consistently while safely handling any unseen categories. The code verifies that the encoded new data has the expected size, 3 rows and 2 columns. If the dimensions are different, it raises an error to flag the problem immediately. This early check helps catch encoding issues before they cause later processing errors. We first get the encoded feature names for the payment column, then use them to build clear data tables for both the training data and the new data. The encoded values are converted to integers, so the results are easier to read and interpret. This makes the transformed categories easier for beginners to understand. The code checks the Scikit-Learn version, then shows which categories the encoder learned from the training data, and which baseline category was dropped. It prints the encoded training and new payment types to show how the transformation works. The key point is that the dropped cash category and the unknown crypto category both produce all zero encodings, showing how the encoder represents the baseline and unseen values. This example shows how Scikit-Learn one-hot encoding works when one category is dropped as a baseline. For payment types, the encoder learns card, cash, and debit, then drops card because it comes first alphabetically. The output reports the learned categories, the dropped baseline, and the encoded training and new data. It also shows that unknown categories such as crypto are handled without error and receive the same all-zero encoding as the dropped category. Encoder pipelines. Target encoding. Target encoding converts categories into numbers by using the average target value for each category, such as an average home price for a neighborhood. It is useful for features with many unique values because it avoids creating many sparse columns while keeping predictive information. In a pipeline, it learns these category mappings from the training data and applies them consistently to new data. Target encoding can leak target information into features if it uses a category's own outcome, making training performance look better than it will be on new data. To reduce this risk, use safeguards such as cross-validation-based encoding, smoothing, and keeping training and evaluation data separate. Smoothing is especially important for rare categories, where simple averages can be unreliable, and these protections should be built into the model workflow. Using target encoding inside a column transformer lets you apply it only to high cardinality categorical features, while handling other data types with suitable preprocessing, such as scaling or one-hot encoding. Keeping these steps in one pipeline makes preprocessing more consistent, supports cleaner cross-validation, and reduces manual errors. This creates a workflow that is easier to evaluate, inspect, and deploy. Python code. Target encoding. This example shows how target encoding can be used safely inside a pipeline. A column transformer sends different columns to the appropriate encoders, while cross-validation evaluates the full preprocessing process and helps prevent target leakage. We import key Python tools for building a machine learning workflow, NumPy and pandas for data handling, and Scikit-Learn for modeling and evaluation. The setup includes tools to pre-process different columns, encode categorical features, combine steps into a pipeline, and assess performance with cross-validation. Logistic regression is then used as the main model for binary classification. We begin by setting up a small dataset with mixed feature types. A fixed random seed ensures the generated data is reproducible, and the dataset is set to contain 120 rows. The dataset begins with several store identifiers, representing a high cardinality categorical feature suited for target encoding. A random selection process then assigns one store identifier to each row, creating a simulated dataset where stores are distributed randomly across the observations. We create a region label for each of the 120 rows by randomly choosing from north, south, and west. Because there are only 3 possible region values, this feature has low cardinality and is well suited for one-hot encoding. This helps simulate a realistic dataset where each record belongs to a specific region. The content defines a store risk mapping that links each store to its churn risk value, then expands it with more stores. It also defines a regional adjustment that changes churn probability by region, with north slightly lowering risk, south having no effect, and west slightly increasing it. We build store-level probabilities from each store's risk value, then adjust them by adding the appropriate regional bonus. Afterward, the probabilities are limited to stay between 0.05 and 0.95. This keeps the values realistic and prevents extreme probabilities from distorting the model's predictions. A binary churn outcome is generated by sampling from a binomial distribution using each customer's churn probability. The store and region information is then organized into a pandas data frame, creating a structured dataset for later processing and modeling. Before training the model, the code verifies that the data rows and target values have the same count. This ensures every feature row has a matching target, which is necessary for reliable training. If the counts do not match, it raises an error to flag the data inconsistency before model fitting begins. A column transformer is used to prepare categorical features for modeling by applying different encoders to different columns. The store column is handled with target encoding, which turns high cardinality categories into numeric values using the target variable, with a fixed random state for reproducibility. The region column is handled with one-hot encoding, which creates binary features for low cardinality categories and ignores unknown values in new data. A pipeline combines preprocessing and modeling into one ordered workflow. It first applies the prepared transformations, including target encoding for the store column and one-hot encoding for the region column, then fits a logistic regression classifier. The model uses 200 maximum iterations and a fixed random state of 42 for reproducible results. This keeps data transformation and training consistent during evaluation. We evaluate the model with 5-fold cross-validation, measuring accuracy on each fold. The encoders are refit within each training fold to avoid data leakage. Finally, we average the accuracy scores and round the result to 3 decimal places for a clear overall performance measure. We train the pipeline on the data using the churn target, which applies preprocessing and fits the logistic regression model. After training, we review the transformed feature names to see what the encoders created and better understand how categorical data was prepared for the model. We first report the Scikit-Learn version to support compatibility and reproducibility. Then we summarize model performance with the mean cross-validation accuracy, which estimates how well it may generalize. Finally, we show how many features were produced after preprocessing and preview some transformed feature names to confirm that categorical encoding worked as expected. This example shows how to use target encoding in a Scikit-Learn machine learning pipeline. A synthetic churn dataset includes categorical features, where a high cardinality store feature is target encoded and a lower cardinality region feature is one-hot encoded. A column transformer applies these pre-processing steps, then logistic regression predicts churn. Cross-validation evaluates accuracy while helping prevent target leakage, and the output reports the Scikit-Learn version, average accuracy, and a brief look at the transformed features. Sparse encoder output. Sparse output is important when encoding categorical variables, especially with one-hot encoding. A single category feature can expand into many indicator columns, but each row usually has only one active value and many zeros. Storing only the non-zero values saves memory and can make the difference between an efficient workflow and one that is too demanding for standard hardware. Categorical encoders can affect both memory use and data flow in a machine learning pipeline. One-hot encoding often creates many columns with mostly zeros, so keeping the result as sparse data can save space and improve efficiency. However, you should confirm that later preprocessing steps and models support sparse data, because converting it to dense form can greatly increase memory use. In a ColumnTransformer workflow, sparse output matters when combining one-hot encoded categorical features with processed numerical features. The transformer decides whether the final dataset is sparse or dense, which affects estimator compatibility, storage efficiency, and deployment. Choosing sparse output can be important for scalable and reliable pipelines, especially when categorical data creates many mostly empty columns. Python code, sparse encoder output. This example shows how a column transformer combines categorical and numeric features, producing sparse encoder output. It also compares the memory use of sparse and dense representations. We import key Python libraries for data preparation and machine learning. NumPy and pandas handle numerical data and data frames, while Scikit-Learn provides pre-processing tools. A column transformer lets us apply different transformations to different columns. One-hot encoding prepares categorical variables for models, and standard scaling standardizes numerical features for efficient learning. We create a small dataset to mimic high cardinality categorical data. It has 200 rows and a set of 100 unique postal codes, each using a common prefix followed by a number. This gives us many distinct categories to test how well an encoding method handles them. A pandas data frame is created to simulate high cardinality categorical data with both postal codes and ages. The postal codes are repeated to produce 200 rows, while the ages are evenly spaced from 20 to 80 using NumPy. This creates a simple dataset that combines categorical and numeric features for later processing. A column transformer is used to process categorical and numeric features together. The preprocessor is applied to fit and transform the data using the earlier settings. It one-hot encodes the postal codes and scales the age values, producing a transformed dataset ready for analysis or modeling. The code verifies that the transformed data is a sparse matrix by checking for the non-zero element count attribute. If that attribute is missing, it raises a runtime error because the expected sparse encoding failed. This check helps ensure memory-efficient handling of high-cardinality categorical data. The code compares sparse and dense matrix storage. It first converts the sparse matrix into a full dense matrix, then counts how many non-zero values the sparse matrix actually stores. It also checks the total number of values in the dense matrix, showing how sparse storage can be more efficient by keeping only the non-zero entries. To estimate sparse matrix memory use, add the storage needed for its data, indices, and index pointers. Then compare that total with the memory required by the same matrix in dense form. This shows how much memory the sparse representation saves. This output checks the Scikit-Learn version, then summarizes the transformed data by showing its shape and whether it is stored as a sparse or dense matrix. It compares the number of stored non-zero values with the full dense size and estimates memory use for both formats. The main goal is to show how sparse storage can save memory when most values are zero. This script shows how a column transformer can process mixed data types by one-hot encoding postal codes and scaling ages. It is configured to produce a sparse matrix when possible, and the output confirms that most values are zero. By comparing sparse and dense memory use, the script demonstrates that sparse storage can be much more efficient, especially for categorical features with many possible values. The printed results include the Scikit-Learn version, transformed data shape, output type, non-zero count, and approximate memory use for each format. Column transformer workflows. A column transformer helps keep preprocessing organized by applying the right transformation to each type of column. Categorical features can be encoded, while numeric features can be scaled or filled in when values are missing. This lets different preprocessing steps run together in a reproducible way, so each column is handled according to its data type. Using a column transformer for categorical encoding keeps preprocessing consistent from training through prediction. It learns category transformations only from the training data, then applies the same rules to validation, test, and production data. This helps prevent errors such as fitting encoders on the full dataset or changing category order, which is especially important in sensitive models like credit risk and fraud detection. A well-designed column transformer keeps categorical encoding inside the preprocessing pipeline, so it is refit separately during cross-validation and model selection. This helps prevent data leakage and gives more reliable performance estimates, especially for encoders that learn from the data. It also makes the workflow clearer by sending categorical, ordinal, and numeric columns through the right processing steps, which makes the system easier to maintain, audit, and adapt as data changes. Python code, column transformer workflows. Create one preprocessing workflow that handles mixed data types by sending categorical and numeric features through separate transformations. This keeps the process organized and ensures the output columns stay consistent, even when new categories appear. This setup imports the main tools needed to build a machine learning workflow. Pandas handles tabular data, while Scikit-Learn provides tools for splitting data, preprocessing features, and training a logistic regression classifier for binary prediction. A column transformer applies different preprocessing to different columns, using one-hot encoding for categorical features and standard scaling for numerical features. A pipeline then combines these preprocessing steps with the model into one organized workflow. We create a small pandas dataset to model customer subscription data. It includes categorical information, such as region and plan, numerical information, such as monthly spend and account age, and a target field showing whether the customer renewed. This gives us a simple example of working with mixed data types, similar to many real-world datasets. To prepare the data for machine learning, we separate the input features from the target label. The renewal column is removed from the feature data, while that same column is kept separately as the value the model will learn to predict. This makes it clear which information is used for prediction and which outcome the model is trying to estimate. First, the features data is checked to confirm it has 8 rows and 4 columns. If it does not, an error is raised to signal that the data structure is not as expected. This early validation helps catch unexpected data changes before they cause problems later in the workflow. The dataset is split into training and testing sets before preprocessing to avoid data leakage. Using Scikit-Learn's train test split, 25% of the data is reserved for testing, with a fixed random state, so the split is reproducible. Stratifying by the target keeps class proportions consistent in both sets, supporting fair training and evaluation. We first separate the dataset columns by the kind of preprocessing they need. The region and plan columns are treated as categorical features for transformations like one-hot encoding, while monthly spend and account months are treated as numeric features for standardization. This separation lets the machine learning pipeline apply the right preprocessing to each data type. A column transformer lets us preprocess different data types in separate ways before modeling. Categorical columns are converted with one-hot encoding, while unknown categories in new data are ignored. Numeric columns are standardized, so their values have a mean of 0 and a standard deviation of 1. This ensures each column type is prepared appropriately for the machine learning model. A Scikit-Learn pipeline combines preprocessing and modeling into one consistent workflow. It first applies the existing preprocessor to handle both categorical and numeric features, then trains a logistic regression classifier. The model uses a fixed random state for reproducibility and a higher iteration limit to help it converge. Train the model only on the training data by fitting the full pipeline, including preprocessing and logistic regression, to the training features and labels. This lets the model learn patterns without seeing the test data, helping prevent overfitting and giving a more reliable evaluation on unseen data. We create a new pandas data frame to represent customer data with region, plan, monthly spend, and account age. The categorical fields include values such as central, north, pro, and basic, while the numeric fields capture spending and account duration. This lets the same preprocessing pipeline transform the new data and support predictions, even when it contains an unseen category such as central. First, get the feature names learned by the preprocessing step to see how the original numeric and categorical data were transformed. Then apply the same preprocessing to the new customer data so its features match the training data. This consistency is essential for making reliable predictions. Use the fitted preprocessing and modeling pipeline to make predictions on new customer data. Then measure accuracy on the test dataset to see how well the model performs on unseen data. The output checks that the machine learning workflow ran correctly and reports the key results. It shows the Scikit-Learn version, the number and sample names of features created by preprocessing, and the shape of the transformed new customer data. It then summarizes model performance with test accuracy and displays the predictions for the new customers. This script shows how to build a reliable Scikit-Learn workflow for mixed numeric and categorical data. It splits the data to avoid leakage, applies one-hot encoding to categories, and standardization to numbers, then combines these steps with logistic regression in one pipeline. The same pipeline trains the model, handles new data consistently, and safely manages unseen categories. It reports key results such as transformed feature information, test accuracy, and predictions for new customers. In this lecture, you learn to encode categorical features using ordinal and one-hot strategies, handle unknown, infrequent, and redundant categories in practical datasets, and integrate categorical encoders into ColumnTransformer workflows. In the next lecture, Lecture B, we will go over imputation targets.
Thank you for your attention. See you all in the next lecture.